a special session where the TAs who graded each question, who knows the answers, will explain the answer for each question and also explain grading rubrics, and so why you get the score that you get. And so we'll arrange that session this week. Yes?
Do you have like the average on the midterm or like?
Yeah, we'll release that too. We'll release that online. Okay. The statistics, right? So average standard deviation, yeah, we'll release that too. Okay. Yeah, so probably this Friday, right? So we'll book the meeting rooms and so come join us this Friday, and if you want to learn more about the exam papers and the answers. Okay. So yeah. So today we are going to. So this is the last part of virtual memory management, and we'll wrap this up, and we'll start talking about the file system. Okay. All right. So previously we were learning demand paging, which is essentially using virtual memory as a cache for external storage. Right? So you have a bunch of processes in your computer, and they are using more memory than what your computer really has. And the physical memory your computer has might be 4 gigabytes, but you have a bunch of processes, and their combined memory usage might be 20 gigabytes, for example. Okay, and in this case, you are going to swap out the pages that are not actively used to disk, and keep only those pages that are actively used in physical memory. In this way, you are providing more virtual memory than physical memory in a computer. And we learned a few techniques that enables this demand paging, efficient demand paging. One is page replacement. That is the key technique that we studied, which is an LRU approximation algorithm, called clock. And we also mentioned there are other techniques like prefetching and memory allocation that is part of the demand paging process. But we are not going to dive very deep into it. Right? So traditionally, the most studied technique is page replacement. Okay. So there's one last thing that we did not discuss is thrashing. Okay. So yeah. So this is the definition of thrashing. Okay. So it is a vicious cycle type of behavior that drops your machine's performance gradually. Okay. So it happens like this. If a process does not have enough pages, then page fault rate is very high. Right? What does this mean? So if a process does not have enough page, it needs to trigger page fault, meaning that it has some page that's on external storage. It triggers page fault to swap in those pages. And this process is very heavy, or more accurately, it's I/O heavy. Right, so you need to do this disk memory I/O to swap out dirty pages and swap in this new page that you want to bring into memory. Very I/O heavy. And Right, so you need to page fault to get the page on disk and replace the existing memory physical frame. And unfortunately, this could happen, right? If the memory is very limited, it is possible that this physical page in memory that was just replaced out will be quickly referenced in the near future, right? Very soon. Okay. One very contrived example is that suppose you have a process that access 3 pages, 1, 2, 3, right? And unfortunately, the amount of memory allocated to this process is just 2 pages. And more unfortunately, the access pattern, memory width pattern of this process is 1, 2, 3, 1, 2, 3. It is a circular pattern. Okay, and if you use first in first out, again, right, so if you use first in first out algorithm, every access will trigger a page fault, because it replaces a page that will be used in the near future. Okay, even LRU cannot completely solve this. Right? If you have sufficient number of pages for a process and sufficiently limited memory allocated to a process, this will happen. Right? You replace a page that will be very quickly referenced in the near future. Okay. So this leads to low CPU utilization. Right? Why does this lead to low CPU utilization? These consequences are interesting. Right? So the page fault, this is very easy to understand. Right? So we have studied page fault and replacement algorithm in detail, but the consequence is interesting, right? Why does it lead to CPU utilization very low?
Because the CPU is constantly blocking
Due to I/O, right. Swapping is mainly I/O, right? If suppose in this case, let's say you have 100 processes and a large number of processes in your computer. Each one of them only gets a small piece of memory. Okay. In this case, all of the processes will do this kind of thrashing, and they will be mainly doing I/O. Because all the processes are mainly doing I/O, then your CPU is mostly idle. Right? Most of the time, it's just the entire computer is just doing I/O. Okay, so this leads to low CPU utilization. Okay, and when CPU utilization is low, what do you usually do? Right? So there are 2 scenarios. There are 2 scenarios where you can have low CPU utilization. Okay, and why OS can be confused, right? This just says that the OS is confused, right? In this case, OS thinks that it needs to increase the degree of multi-programming. Right? This means that low CPU utilization can imply 2 things, right? One scenario is that you really need to increase multi-programming. The other is that thrashing. Right? Both scenarios could show manifest as low CPU utilization, and the OS is confused. Anyone want to try to explain, right? What is the other scenario that could also have low CPU utilization and make OS think that it needs to increase the multi-programming? Yes.
high I/O usage.
High I/O usage is limited with a small number of processes. Right? That's on the right track. Right? So imagine you have one process. Let's suppose you just have one process in your computer, and this process will be be doing I/O for most of the time, right? Because I/O is slow, computation is usually fast, right? So most of programs spend most of their time on I/O. Right? Of course, there are scientific computation; those kind of programs will spend most of the time on computation. But you can imagine, because every process alternates between CPU usage and I/O, right? If you have a limited number of processes, extreme speaking, right? If you just have one process, you may have 50% of the time CPU is idle because the process is blocked on I/O, so it's not doing anything. Okay, and because of that, right? Multi-programming, the entire multi-programming technique is invented because of this. Right? Because if you add another process, so that when the first process is blocked on I/O, the second process can use the CPU. Right? In this case, you multiplex CPU and increase the CPU utilization, so that your computer is not idle most of the time. You don't want to waste your computation resource. Okay, so this is why OS can get confused. Right? One reason for low CPU utilization is that you have very limited multi-programming. You have, let's say, only one process running in computer. Right? So CPU utilization is low, and the OS might think, okay, I have a lot of jobs that I haven't run. Let's pull in these jobs, admit these jobs, and start running them in multiple processes. That way, we won't let the CPU sit idle. Okay, that's one genuine scenario. The other scenario is this one, right? Thrashing, as we have explained. We have too many processes in the computer, and each of the processes is only using a small amount of memory. Right? You can also run into this thrashing scenario and cause low CPU utilization. Okay, so this signal, low CPU utilization, this signal itself, by itself, can confuse the OS. OS cannot tell whether it needs to increase multi-programming or decrease multi-programming. Okay, so if the OS made the wrong choice, right? If it mistakenly think that we need to increase multi-programming and adds another process to the system, what happens? So if it adds another process, right, it thinks CPU utilization is low, let's add another process to use the CPU. Yes?
You get more thrashing.
More thrashing. Right? So because this process that's just added to the system will need to be allocated with some memory, which means that, for example, in the dynamic memory allocation OS, it needs to take some memory away from the other existing processes. It means that all the other processes they will thrash harder, right? And this process that's newly added, it likely will not be able to get sufficient memory either, so it will also thrash. Okay. Right, so the in the early days, this really happens, and it's a big problem. So this is the system behavior under thrashing, right? So this is the CPU utilization on the y-axis. The x-axis is the degree of multi-programming. So when you increase the degree of multi-programming, in the beginning you get higher and higher CPU utilization, but when you pass this point, when it starts thrashing, the more process you add, right? So the worse the thrashing is. Okay. Right, so you trigger this vicious cycle and crash the system. Okay. All right. So how to solve this? How to solve this? Yes.
You could like kill the process using a little memory.
Sorry?
You could like kill a process.
Kill the process, yes. Right. So that's a very straightforward solution. it just tells you that CPU utilization as a signal by itself is not sufficient. You cannot rely on CPU utilization to tell whether the system is has too little multi-programming or has too much. Right? So if you can detect when thrashing starts, then you can kill processes. Right? So if you can observe, okay, thrashing has started, then just see that, okay, we have too many processes. Some of you need to stop. Right? So, for example, those background tasks that does not have a very high priority, let's put you guys to the background. Stop, pause there for a second, and let me finish the other process first. Okay, so but this requires accurate detection of thrashing, and it's possible. Right? Why is it possible? Right? If we use only CPU utilization, it might be hard. Right? Because only if you see that at this point and this point, the CPU utilization is the same. Right? And you have two different points have the same CPU utilization, you cannot tell. Right? What else? What is the other signal that you can use to differentiate whether the system is has too little multi-programming or it has too much? Take a guess. We have 2 points. One, let's say here, the system is already thrashing. And one is here, the system is has very low multi-programming, so you might want to increase processes. When you reach here, you want to decrease process. Decrease the number of processes. How do you differentiate these two? Take a guess. Yes.
Maybe by setting a max number on the number of processes.
Sorry, can I say it again?
By limiting the number of processes.
Maybe the number of processes. Okay, that's a good guess, but the question is, how do you differentiate these 2 points? And not, if you can, how to differentiate these 2 points to detect the thrashing really happened? If you know the thrashing happened, then you can limit the number of processes. The question is, before that step, how do we know? We need to start limiting the number of processes. Yes.
Could it be like the rate of page faults?
The rate of page faults, exactly. Right. Page fault rate, or you can also monitor I/O. Right. So if your CPU utilization is very low, but your disk I/O is saturated, right? Then you might be in thrashing. Right? Especially if you add page fault, right? You do a lot of page faults, right? Most of the I/O is due to page fault, not normal read. Right? So it's due to page fault. Okay. So yeah, add some other signal like I/O and page fault, then you can differentiate these 2 points. So you can detect when thrashing starts. Okay. Yeah, so you can do that. That's a very simple solution, right? So detect thrashing started and then kill some processes or deprioritize some processes. Okay. But there's another more fine-grained, right? More fine-grained solution, right? So to this problem, which is called working set, right? Or work set with locality. Let's explain what locality means. So first, why does demand paging work? Right? Why is it the case that we can use a very small amount of physical memory as cache, right? And to provide service for a large number of processes? Okay, because in your computer, right? In any modern computer, there are hundreds to thousands of processes running at a time. Okay, and the virtual memory, the address space for every process is 64 gigabytes at least. But your computer, and most of our computers do not have 64 gigabytes, right? Unless you're working on a server machine. Right? So not to, let alone that you have hundreds to thousands of processes, each of them is supposed to have 64 gigabytes of memory dedicated to itself. Okay, so without demand paging, if you really want to fit these hundreds to thousands of processes, right, you can imagine the amount of memory that you have on one computer is the terabytes. Right? Okay, so the physical memory we have compared to the number of processes that we run on a modern computer is very small. Right? 16 gigabytes, 32 gigabytes, 48 gigabytes, right? This is still very small compared to the number of processes running on your computer. So why does it work? So the ratio might be 1%, right? So you might have, if you sum up all the virtual memory space of the processing on your computer, right, compared to the real physical memory that you have, the portion ratio might be 1%. Right? You really have only 1% of the memory that is needed to cover all the processes of virtual memory. Okay. Why this can actually work? The reason we briefly mentioned before is the locality. Okay. What does the locality mean? Can you take a guess? I think we briefly mentioned this before. Right? What does locality mean? The locality is a key that makes demand paging or any caching, any cache to work. What does locality mean? Yes.
Is it that if you're accessing from one memory, likely that you'd be accessing from the really closely surrounding memory?
Right. That is one spatial locality. Right? Spatial locality, which means that if your program is accessing memory address 1, then in the near future it's likely to access the adjacent memory locations, like memory 0, memory 2, right? So these places. That's spatial locality. And the other is temporal locality, which means that the memory pages that you accessed in the recent past, right, are likely going to be accessed again in the near future. That's temporal locality. And because of these two locality properties, that is how demand paging can really work. So the programs, your programs migrate from one locality to another gradually during this execution. Okay, so the page fault really only happens at the boundary of these transitions between localities. Okay, and when the transition happens, right, when the transition happens between one locality to the other, you can further reduce the amount of page fault by doing prefetching, which we mentioned this prefetching algorithm before, right? So you don't wait for every page fault to happen. You prefetch a bunch of pages that are close to each other. So that's if you detect the locality is shifting, you do some prefetching. Okay, so this is why demand paging, right? Even though you only have 1% of physical memory compared to the total amount of memory that you need, why it can still work? Because the processes migrates from one locality to the other. Okay, and this is this property is first discovered by many researchers back in 1980s, and later it even becomes a programming practice. Right? The point is, it kind of impact programming um, in return. Right? So in the beginning, they found that many programs have this locality behavior where they access memories around in a closely adjacent set. And this was just empirical observation. But later it becomes a rule, right? In order to make this cache, all the cache system we have in computer work, it becomes a requirement that your program should be written in this way, that most of the time it's only accessing the memories which are close to each other. Okay? So this is even more important in today's machine learning systems. Right? If you are interested in machine learning systems, right? There are a lot of works that build system level software to support machine learning applications. And if you work in that area, you will need to write programs that run on GPUs. And when you write programs run on GPUs, this locality is very important. Right? So the GPUs have many cores, right? Hundreds to thousands cores, and a set of cores will share a piece of memory that's close to it. How do you place the data close to each GPU core and write a program in a way that it only access, most of the time it only accesses memory that's close to these cores? That's very important for the performance of your machine learning application. Okay, yeah. So this locality model is very important. It started as an empirical observation, and then it becomes a rule that everyone we have to write programs like this. Otherwise, the computer just doesn't work. So because inside the computer you have layers of caches. CPU cache, L1 cache, L2 cache, L3 cache, and then right, TLB cache, and then memory as a cache for external storage. And now you have more hardware devices like persistent memory. If you have heard about it, it's a new type of device that you can use as a cache in between your memory and CPU memory and CPU cache. Okay, and yeah, so the entire computer system and the internet works because of layers of cache systems, and these locality is the single most important rule to make this cache system work, and the programs you develop have to respect these rules. Okay, so now why does thrashing occur? Right. Thrashing occurs because the size of the locality set that belong to all the processes in your computer. Let's say you have 10 processes in your computer. Each of them have their own locality set, right? Which means that during a small period of time, what is the memory that is going to access relatively frequently? Okay, and so let's see, every process have their own locality set, but the combined size of this locality set from these 10 processes, if it's larger than the total physical memory you have, then this is going to cause thrashing. Right? And what's the reason? Because every process locality, or it's later we'll see this called working set. So every process working set, inside this working set, the memory pages will be accessed very frequently during a short period of time, repeatedly, frequently. So if you swap out any of these pages in the locality set or working set, the consequence is likely a page fault because it will be referenced in the near future. So when the size of the locality is larger than the total memory size, then page fault is going to happen, has a high chance that page fault is going to happen very frequently, and that's when thrashing occurs. Okay. So what does this imply? What does this imply? So you want to make sure that the process that you keep in memory or you keep running, right, has the total size of their working set or locality set smaller than the physical memory you have. Okay. All right. So this is an example. Let me see. Okay. This is an example of memory access pattern running if I remember correctly, running a few programs. Okay, and you can see that right. So this is the time, execution time. Okay, this is the execution time. This is a page number, right? Y-axis is this page number. Okay, when you read this diagram, you can see that right, what is a working set? What does a working set look like? Okay, so this part, right, this part is likely a working set. What does this mean? Why is it working set? And because during this period of time, right, from here to here, you can see these pages, they are accessed together, right, simultaneously, or close to each other, right, repeatedly, simultaneously, these pages, right, which means that they are in a locality set, or working set, okay? Right, so similarly, the shadow on the upper side also, right, that's a working set. When did the working set shift? Right, when did locality shift? Okay. This is the point. Right, very clearly you see that this shadow did not happen before. This shadow means that suddenly a process or a few processes start accessing this portion of the memory repeatedly and frequently. Okay, so this is the visual illustration of locality and how locality shifts with the time goes up. Okay, so from this diagram, can you tell me what is the smallest amount of physical memory that you have to avoid thrashing in this case, in this specific computer? What is the smallest amount of memory that you have to avoid thrashing? Can give a rough number. You can give a rough number and then expand your reason.
My guess is about 12 pages because that's the maximum amount used at one time.
The idea is definitely right. But the maximum amount of memory used at any point in time, right? So if you look at this diagram, right, you can see that this is page 18 to page 24, right? Let's see, this is right. So it's 6 pages, right? And this is from this part is from page 29 to 34, right? It's yeah, it's 5 pages. sorry, this is 6 pages. This is 7 pages. Right? 7 plus 6, 12, 13 pages. That's the minimum amount of pages that you need to fit this working set and this working set. Okay, and then when it shifts, this working set is smaller, right? So you have from 24 to 34. This is 10 or 11 pages. Okay, so to avoid thrashing, you need around 12 to 13 pages. All right, so that's the idea. So at any point in time, you need the smallest amount of memory you need is need to fit all the working set at any point in time. Okay. All right. Okay. So this is that was the intuition. This is the formula. Right? So but it's explaining the same thing. Essentially, it's saying that at any point in time, you need to have sufficient memory that covers all the working sets. Okay. But we can go through this bullet points slowly. Right? So a working set window, right, is a fixed number of page references. Right? For example, 10,000 instructions, right, during the execution. Okay, and the work set of process, the working set of process PI is the total number of pages referenced in the most recent working set window. Okay. So if this working set window is too small, it does not contain the entire locality. If it's too large, it will contain multiple localities. Right? So if it's infinite, it will include the entire program. Okay. All right. So this D is the total demand frames, right? Approximation of locality. So it's saying that at any point in time, what is the largest amount of memory that you need? Okay. If D, this demanded memory, is larger than the total amount of physical memory you have, then it will cause thrashing. So what you want to do is, as we mentioned before, if you found that the total set of demand pages, total working set is larger than the physical memory, then you start suspending or swap out the processes. Right? Suspend some processes. Okay. Okay. All right. So how do we do this? How do we detect that the total number of working set is becoming larger than the physical memory? Okay. So we previously just discussed a very simple, straightforward solution, which is you track the amount of CPU usage and the number of page faults. If you have a low CPU usage and a high page fault, then you are likely doing thrashing. Right. But here, people studied a more accurate way to estimate this. Right. They really try to estimate what is the current size of the working set of all the processes in the computer, and then compare this size of working set against the amount of memory you have. Okay, so this gives you a more accurate way to predict whether you are doing thrashing or not. Okay, all right. So yeah, approximate the working set with interval timer plus a reference bit. Okay, so what it means is really just every time interval, let's see, 10,000 instructions, you are just collecting the memory accesses during the past 10,000 instructions and treat that as working set. Okay, so yeah, the timer interrupts after every 5,000 time units, and keep in memory 2 bits for each page, and whenever a timer interrupts, copy and set the value of all reference bits to 0. Right? it means that you clean it, right? So every time interval, you clean this reference bit to 0. Okay? But during the past period of time, if the one of the bits in memory, right, if the bit is 1, it means that this page has been accessed during the past 5,000 time units. Right? So all the pages that have been accessed in the past 5,000 time units, they form the working set during the past time period. And this is an approximation of the working set for a process. Right? And of course, it's not completely accurate because you don't know how frequently every page is accessed. During the past 5,000 time units, maybe some pages accessed 1 time, but some other pages has been accessed 100 times. And then obviously they are not the same. Okay. So to increase the accuracy, you can add more bits to record the frequency of a page access, right? And you can reduce the the time period that you use to detect the working set. But yeah, it's essentially an approximation. There's no guarantee. You can improve the accuracy, but there's no guarantee. Okay. Yeah, sorry. Not sure what happened. So yeah, so this is how you track working set and estimate working set. All right. The other approach is what we mentioned before, right? So you can measure CPU utilization and page fault frequency. Right? If you see that CPU utilization is very low and your page fault frequency is very high, then probably you are doing thrashing. Okay, so it's more direct approach than working set, right? And but you need to establish an acceptable page fault frequency and use a local replacement policy. If the rate is too low, then the process loses frame. If the rate is very high, then process gains frame. Okay. What does this mean? Right? So if your process is doing a lot of page fault, it means that it's probably thrashing and you want to give it more memory. Right? If your process is have very low page fault rates, it's not requesting more memory very often, then it can lose its frames. OS can reclaim its frame and allocate to other processes. Okay. Very often people use this. It's a simpler strategy than working set. Okay. Right. So the relationship between working set and page fault rates. Right? There's a direct relationship between working set of process and its page fault rate. Right? This is very obvious. Right? So if it's a working set is very high and its allocated memory is very small, then the page fault rate will be very high. And the working set of a process changes over time as it peaks and valleys over time. Right? So and because the working set changes, you can dynamically adjust the amount of memory that you allocate to every process. Okay, that is the end of demand page. I haven't uploaded the slides for file system, but I'll do it very soon. Okay. Okay. We'll quickly give an overview of file system, right? Because later labs, right? So later labs will start working on file system, right? Okay. So, how many people knows about file system internal, right? So how does file system work? And obviously the user APIs, right? What is its structure from a user perspective? And it's internal, right? So how is it organized internally? So how do you know? How much do you know about file system?
I think from the user's perspective, there's like the files and directory and everything, but then from the internally it's used blocks.
This box, yeah. So that is correct, and so from a user perspective, right? So it's very easy to understand, right? It's organized in a tree structure, right? So your file system, to you, it looks like a tree, and every internal node of this tree is a folder or directory, right? And every directory can contain multiple files and other directories, so it can be recursive. That's how it forms a tree. Okay, so that's how a file system looks like to a user. Right? But internally, because on the disk, right, this file system is an organization of external storage. Right? On disk, everything is just blocks. So in external storage, in hard drive is divided into blocks or sectors. Okay, and so it does not have this tree structure. Right? How do you map this user's view of tree structure to the blocks in the external storage? Right? That's how file system is designed. Right? That's a core question that file system design answers. And map this tree structure that human uses to the block level storage in the external storage. How do you do this, and how do you do it efficiently? Right? When you, and also safety. Right? So that's the critical question that you answer in file system design. All right. So we'll first start from the APIs. Right? So the users must be able to do these things using the file system API. Right? You need to be able to create, modify, and delete files. Right? This is very obvious. And you need to be able to read, write, and model file contents. Right? And share each other's file with proper authorization, transfer information between files, refer to files by symbolic names. Right? This is symbolic links. There are hard symbolic links and soft symbolic links. And retrieve backup copies of files lost through accident. Right? So you need to be able to persist these files, okay? And see a logical view of their files without concern for how they are stored. Right? You do not want to know that your files are stored as a sequence of blocks on external storage. You do not want to manage them. As a user, all you want to do is that when I read the file, I can read the file line by line. Okay. So these are the requirements when you design a file system. Okay. All right. So the file structure. Okay. So there are different ways to organize a file. Right? One, the simplest approach is to organize a file as a byte sequence. Right? So it's a sequence of bytes, and you can read or write a number of bytes, and you can read and write starting from one position in this byte sequence. For example, I start reading from position 10, and I will read until position 20 from this byte sequence. Similarly for write, I want to start modifying at position at Z20, and I will overwrite 10 bytes in this byte sequence. Okay, this is one way to organize a file, and it was used in the very early days, and even today, right? So remember, in network protocols, whenever you communicate with another machine, you need to do serialization. You serialize a structured in memory object into a byte sequence. That's how you can send over the network to another machine, and the other machine will read this byte sequence and deserialize it, reconstruct the object that the data that you used to construct the network message. Okay. All right. So byte sequence. All right. Unstructured, and the user program need to decide what it means. So another type of file structure is a record sequence. Right? You have more structure in this organization. Right? So which means that you have a sequence of records, and you know that inside these records, what are the data members? Right? You have more semantic meaning embedded in this structure. It's fixed length, and you can read or write one record at a time. And every record has a few data members that you already know. Okay, this is another way of file structure. And tree. Right? The third way is you have trees, and you have a tree of records. Right? And every record has a key that is used to organize this tree. Okay, and you can read, insert, delete a specific record, and so it's still used on mainframe computers. Right? This is some approach to organize files. Right? A lot of them are used developed in the early days. Some of them are still used today in specific scenarios. Okay. All right. So how to use a file? Right? How do you use a file? There are mainly two patterns of file access. One is a sequential access, which means that you read this file starting from the first byte until the end, for example. Right? So read all these bytes in order. Okay, tapes, continuous media files. Right? So you, I think when you are playing a video or a movie on your computer, when you're playing a music on your computer, this is the access pattern. You are sequentially accessing the music file or the movie file. Okay. The other is random access. Right? You read bytes and records out of order. Or what it really means is that you can provide a position when you are trying to access the file, and the API allows it to directly return you the data at the specific specified positions. So this is what random access means. Okay. You read bytes or modify content of a file at specific positions. Okay. So it's very essential for some applications, such as databases, you need to seek to the location that you want to modify, and then start modifying or start reading from that location. Okay. To implement file system, right, to map this file system API functionality to the how they are implemented on disk, right, external storage, there are 4 key aspects in the design. Right? First is layout, right, how this file system is stored on the external storage, and the second is allocation. Right? How do you do allocation, and how do you release allocate a file, how do you release it, and how do you delete it, and management of free blocks, right? Because this external storage media has many blocks, right? Similar to memory. You have a list of free blocks that you can use to allocate to new file or to old existing files when they are doing append. Okay, so management of free blocks and the management of directory. So you can move files from one directory to the other, and that's also important. Okay. So how do we implement this? The answer to these questions defines your file system. Okay. Right. Here are some example strategies of file allocation. Okay. So continuous file allocation, linked list class table, inode. Right. This inode is the most popular organization of files in modern computer. Okay, we will explain this inodes approach in detail. Right? The others will just quickly skim through it. Okay, right. So continuous allocation. Okay. So you have a disk, and right, so this disk has many blocks, right, sequentially organized in this disk. Okay, and for file 1, you just put it in block 1, and you put it, give it a start location and length. Right? For example, if when I'm creating this file, I said that my file starts at block 1, and the length of my file is 10 blocks, and that's my length. In this case, maybe I will have 1 block for this file. Okay, and then when I allocate another file, I just put it right. Continuous allocation means that I just allocate the second block to file 2. Right? So all the files are allocated continuously in this external storage. Okay. The downside is very obvious. You must know the file size. Okay, so because you specify the start of the file and the length, will allocate the file. Okay, so this downside is very, very critical. Right? What is the reason? Because when we are using files, we modify these files very frequently. Right? We might truncate the file, we might delete content, we might add content to these files, and which means that the size of the files that we use, a lot of them are dynamic. Okay, so if we use this fixed length for each file, then the easiest figure is that I'm trying to append content to this file, but it cannot be appended anymore because the length is reached. Okay. The other figure is that, okay, I have a file that I modified, I deleted content, then this creates fragmentation, which is the small pieces of disk storage that is not used by anyone but cannot be allocated. Continuous allocation. This is a very early days, people could use this, but it's not ideal. Okay, so to improve on that, people have developed linked list allocation. Right? So you have an index with address to the first block. Right? So in this directory you have a file, right? This is supposed to be the file name, and this file has a link, has an address linking to the first block that contains the first piece of data. Okay, and then this block, first block of this file contains a link to the second block of this file, and so on. Right? You have a linked list of all the data blocks. All right. So in this case, every file has an index of the first of the address to the first block. Right? So every block points to the next block. Right? So this design is much better. It can grow files dynamically. Right? So linked list is has this benefit. Right? The downside is that random access is very slow. Now you can imagine that if I want to access some data in the third block here, then I need to traverse this linked list to find that piece of data. Okay. In the previous sequential allocation or continuous allocation approach, you can directly calculate the block that you need to access, and you can directly access that block. And the other downside is that you still have internal fragmentation, and you have incomplete block sizes, and it can be unreliable. Right? It's possible that your linked list breaks and loses some blocks in the chain. Okay. So after that, people further improved it by using linked list plus a table. Right? So this is already very similar to the table that you are using in Xenu. Right? If you remember, in Xenu you have such a list. You have the current process index, and then the next process on the list. Right? So this is essentially the same. Right? We have a table, and this table has the current data blocks ID and the next data blocks ID. Okay, so all the pointers are stored in table, right? The current block and the next block, and next equals -1 indicates this is end of the list. Okay. Right. So what does this mean? Right, so using this table, right, what is the improvement? What is the improvement of this? Because this, yes.
You don't have to actually sequence.
You don't have to actually traverse the linked list of blocks, because the pointers are not stored with the blocks. The pointers are stored in this table. This table is very small, right? Maybe just one block at the beginning of the disk. That's it. And you can load this small table into memory. Okay, and use it to repeatedly access to search for the data that you want to access. Right. So this small table can fit in memory very easily, and you can just you still need to do this linked list traversal, right? But you are traversal in this table instead of reading one block at a time from disk. Right? That's a benefit that you'll get. Okay. All right. So this table, right? So it need to be stored in memory, right? So but you can imagine do a backup envelope calculation with 20 gigabyte disk. You can have a very large table. Okay, so so this cost of the table is not small. And that's only 20 gigabytes of disk. And nowadays, I think many of us have 1 terabyte bytes, right, SSD even on our computer. Right? So yeah, this approach does not scale with large disk. Okay. All right. So to avoid that, right, so people invented this thing, I know, or right, in the beginning it really means that it's indexed. I know, right, index node. Okay, so you can understand it like that. So you can associate every file with a data structure called inode. Okay, and this inode is a table of the files blocks. Right? It's not a global table anymore. This inode contains a table that is specific to this file. Okay, and you're essentially splitting. Right? So previously you have a huge table for all the blocks in your computer, but now you have a per file tables, right? And this table is stored in this data structure called inode. And you are only going to load the needed inodes, right, for open files into memory. Okay, that's a core idea behind this inode. Right? So it's essentially splitting this huge table recording the linked list of data blocks into per file linked lists, so that you can dynamically decide which of this table need to be loaded in memory. Okay. Right. So it reduces the amount of memory that's needed for open files, right? You only need to set a maximum number of open files. Okay. Right. So yeah, this is let me see whether this is the best. Yeah. And let's use this one. So this is inode. Every file has one inode data structure. Right? So this is its attributes. You have a file type, size, owner, blah blah, etc. Right? So these are just metadata. Okay. But the most important thing is this table. Right? So you have the list of all the blocks that belong to this file. Right? This table references, right, stores the addresses of all the blocks that belong to this file. Okay? You have the address of block 0, the first block of your file, the address of block 1, right, the second block, and address of block n. If this is not sufficient, you have indirect links, right, which means that, so here, this one level indirect means that, okay, this is referring to another block, and every entry in that block references another data block. Right? This is single indirect. Double indirect means that there are two levels of blocks. Triple indirect, three levels of blocks. But let's actually let me explain this in more detail. What does this mean? I think probably this might be the last thing that we explain, right? So what is a direct block? What is an indirect block? What's the difference between them? Right. Let's take a guess. What does so the earlier ones, they are direct blocks. What does it mean? Right. What is the difference between direct blocks and indirect blocks? Yes.
Indirect blocks is like a page table kind of thing. It leads to other pages, other blocks. One block that has addresses of other blocks.
Mm-hmm. That's right. What is the direct blocks? The first.
Direct is direct address of a block.
Address of block. But what does that block store? That's the important thing. What does so you mentioned that's one thing that's correct, right? The indirect blocks stores addresses or pointers to other blocks, other direct blocks. But direct blocks, what do they store?
Like pieces of a file, like pieces of a file.
exactly the content of the file, right? Address of block 0 to block n, those are direct blocks or data blocks of file, right? So more accurately, right, they are usually called data blocks of a file, meaning that they are storing the content of the file. Right? Indirect blocks, they are not storing the content of the file. They are storing a list of pointers to data blocks. Okay, and this is very similar to the multi-level page table design that we have studied. Right? Double indirect means that okay, there are 2 layers, so the next immediate layer is still indirect block. Okay, so this is how you can use a small table to store all the blocks that are belong to one file. Okay, all right. So this is I think some of the core concepts that you need to understand for file system, and on Wednesday we'll continue learning about file system. We'll quickly settle for the time that you can get your exam paper, and I think probably this Friday sometime, and request for regrading, and come join us on Friday. Okay, all right, thanks. That's it for today. If you have answer questions, comment.